Hi students, welcome to Structural Engineering lectures and welcome to the new playlist on the design of steel structures limited method conforming to IS 800 2007. In today's class we shall see the designs of the welded connections, that are the simple welded connections, a few design examples. 4 design examples we will see in this part 2. In today's class we shall see one problem of design of a plate subjected to tension, right? First problem. Second problem is design of an angle connected to a gusset plate, right? The third problem is design of design of a welded plate girder. The connection between the flange and the web, as well as that of the flange and cover plate. And the fourth problem is the design of a hollow circular tube connected to a gusset plate, right? Therefore, which is subjected to combined bending, torsion, and shear. Right? These 4 problems we will see in this class, student. Right? Whereas in the previous class we have seen this simple welded connections, a few design examples. I hope you are enjoying the discussions, right? If you are enjoying the discussions, don't forget to click like, comment, share, subscribe to our YouTube channel, right? Now, before we go for the actual discussion, student, now let us see the brief profile of mine. That is, I, Dr. D. Rupesh Kumar, has obtained my BTech Civil Engineering from Nagarjuna University in 1994 and MTech Structural Engineering from JNTU Hyderabad in 2000 and PhD Structural Engineering from JNTU Hyderabad in 2009. Presently, I am working as Associate Professor in Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. Right? My research areas include reinforced cement concrete designs, steel designs, structural analysis, front element analysis, earthquake engineering, bridge engineering, structural optimization. I have published 45 research papers in international and national journals and conferences, organized 3 national international conferences and 11 national conferences and workshops, attended 43 workshops, visited 2 countries and delivered 13 guest lectures, edited 3 books, and supervising 14 PhD scholars and supervised 30 ME scholars. I am actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 designs of RCC, steel, composite, low-rise, high-rise, multi-storied buildings and road and rail bridges. Right? Once we examine this brief profile, student, let us move quickly to the top. What we are going to see in today's class. Now let us see those schematics. Right? That is how the very first design. We will see a flat, right? A flat are subjected to a tension force, and what is that overlap required, right? That is the first problem, student, right? This is how that overlap length required on either on 2 sides as well as that of the 3 sides, right? That is another schematic, right? And we'll also see the design of an angle, right, connected to one side of a gusset plate, right? One side of a gusset plate, right? How much of length of overlap is required? How much of length of overlap is required at the top as well as the bottom, like this. Another schematic, right? The same is another schematic, right? And we'll also see another problem wherein a hollow round tube, right? A hollow round tube is connected to a plate. Therefore, how much of now this is subjected to a combined bending, torsion as well as shear. Therefore, we need to design this weld, right? Subjected to the 3: shear, bending, and torsion, right? And we'll also see another problem wherein this is how much of the overlap is required. How much of the overlap is required for the Indian standard flat when connected to the top a gusset plate like this, a gusset plate, right? These are the 4 problems we'll see, right? Now this is how even we'll say how much of length is required at the top and bottom, right? And also how much of length is required, here, right? Either when provided on 2 sides or on the 3 sides, right? These 4 problems we'll see in today's class, student. Now let us see the numeric problems at a quicker pace, right? Now let us move to the numeric problems. I hope you are enjoying the discussions, right? Now let us see a first problem, right? A tie member 75 mm by 8 mm is to transmit a factor load, right? This is of 75 and 8. This is of 75 is the width and 8 mm is the thickness. 8 mm thickness is to transmit a factor load of 145 kilonewton. Design fillet weld and necessary overlap with the following conditions, right? 1, the overlap on 2 opposite sides, right? Like this, 2 opposite sides, and using the shop welding, and the second bit is welding done on 3 sides, right? This as well as this, right? And shop welding. And the third one is welding done on all the 4 sides. All the 4 sides mean this 1, 2, 3, and on the rear side another weld, right? That is on all the 4 sides, but site welding. Therefore, now I'll open the IS 800 2007. Then once it is a shop welding, then we know the partial safety factor for that weld. Gamma MW is equal to 1.25, student. Whereas for the site welding, the partial safety factor for the weld is equal to 1.5. We have already seen that, right? Now let us see. Obviously, we need to provide the end returns to prevent the failure in the tension zone, right? To a distance of 2s as per the code, right? And that we all seen the other day, right? As per the IS 800, right? Like this, right? End returns, class 10.5.1, not less than twice the size of the weld, right? Now that we'll see during the problem. That is how the end return, right? Now, whereas this is a given data, student, right? 75 by 8 mm is a tie member, right? And we need to connect it to a gusset plate, right? And also what is given is use Fu 410 grade steel. Therefore, the Fu for the steel is equal to 410 Newton per mm square, and it is subjected to a factor tension force of 145 kilonewton. And now what I am assuming is that here the tie member, this thickness is already 8 mm is given, but once we connect a tension member to that of a gusset plate, the main concept is that the connections should not fail. Therefore, if it is true, then the thickness of this gusset plate should be more than that of the thickness of this tension member, right? Therefore, now I'll assume that the thickness of the gusset plate is equal to 12 mm. This thickness is equal to 12 mm, right? This is my assumption. You may differ also, right? Or even you may say 10 mm, because even 10 mm is also greater than 8 mm. It is okay then, right? Then, however, we'll see the first bit wherein the welding should be done on 2 sides, right? Top and bottom, right? With end returns, right? Like this, right? End returns, right? Then, however, once we see this, what is the maximum thickness of these, right? 8 mm, as well as the gusset plate is 12 mm. Therefore, the maximum size out of these two is equal to 12 mm. Therefore, once I go to this table 21 of IS 800, student, then I do have for this thicker plate, right? 10 to 20, right? It is in between. Therefore, the minimum size from this table 21 of IS 800 size should not be less than 5 mm, right? Once I note that, then I'll say that even from this figure 18 of page 80, let me go to that page 80, student, right? This is how now the code says that even the maximum, right? This, right? Even the fillet weld from this figure 17, the maximum the size of the fillet weld should be less than 1.5 times that of that thickness of this plate. Therefore, now even recall this. Hence, I will say that the size should not be more than, right? Because 8 mm is my the plate thickness. Therefore, 8 minus 1.5, it is equal to 6.5. Therefore, the size should not be less than 5 mm and should not be more than 6.5 mm. 6.5 mm. Therefore, now I'll say that okay. Let us say size is equal to 5 mm. That is what my assumption, right? Then if it is true, then now I'll say that the even once I apply the fillet welding like this, right? Fillet welding, then obviously that fillet welding is 90 degree to the top of this surface what we are going to weld. Therefore, from the code book and from table 22, of page number 78, now I have to have this k value as 1 by root 2, which is equal to 0.7, or otherwise also the code says that for fillet weld, the size should be taken as this one, right? 0.7 t, right? Therefore, either of the two is true, or even you can go to this this table also, right? Therefore, here it says that even for 90 degree it is 0.7. Either of the two is true, right? Once I note down that, then I'll get the effective throat thickness. Effective throat thickness is equal to 0.7 multiplied by S, which is equal to 3.5 mm TT, rotated by TT, right? However, you please see that once this is subjected to tension force, obviously the weld which is provided here will be also subjected to the shearing action, right? Therefore, it will fail in shear criteria, right? This tension in the main member will cause failure in the weld in the shear criteria, right? Therefore, now I'll note down what is the permissible shear stress in the weld. Now that is how it is given in the code book as in any case the weld, right? Fillet weld, FWD is equal to FWN divided by gamma NB, where FWN is a nominal strength of the fillet weld, FU divided by root 3, and gamma MW is equal to the partial safety factor as per this table 5, page number 30. Just now we have seen those values, right? Therefore, now I'll recall that formula. Hence, permissible shear stress is equal to FWD is equal to 410 divided by root 3 multiplied by 1.25 the denominator, right? Now it works out say around some 187 Newton per mm square, right? Therefore, now if the tension member is to be overlapped over this gusset plate, right? Now let LW is the length of the total length of the weld required, right? Weld required. Therefore, now I have this from this formula of the code book right? Now the code says that in any criteria, right, FARQ is equal to P divided by LW multiplied by TT. Therefore, now for either shear force or tension force or any other force, right, or shear force, right, or axial force, under these three criteria, the formula is the same. Therefore, I'm recalling that formula and substituting the shear force in the weld, or shear force to be carried by this weld, right, is equal to 145 kilonewton and 10 newtons, right? And that is equal to permissible shear stress in the weld multiplied by shearing area is nothing but length of that weld, LW multiplied by effective throat thickness is equal to 3.5. Therefore, now I'll get the total length of the weld required is equal to 218.77, right? However, we need to provide this in the top as well as the bottom, right, in both the joints, because I am having a connection only possible at top as well as the bottom here, at the bottom, right, like this, right, bottom and top, right, Therefore, that is how the length of the weld either at the top as well as the bottom required is equal to that actual length required divided by 2, or it works out say around 110 mm approximately. However, that length should not be less than this width. However, this width of this flat is equal to 75 mm. However, this 110 is not less than 75 mm. Therefore, okay, right? That is how. Even now you provide an end return like this of 2 times size is equal to already 5 mm. Therefore, 2 multiplied by 10. Therefore, you provide a end return of 10 mm here, 10 mm here, in addition to 110 mm at the top, as well as 110 mm at the bottom, as well as a end return of 10 mm like this, right? Therefore that is how the first design student, right? Therefore the total length provided is equal to 219 plus 40, right? Approximately it is 259 or say 260 mm, right? That is how if it is provided on two sides, right? Whereas if the weld is provided on three sides, second bit, right? Second bit, then however here the length will not change, right? However, just now we have seen in the first bit that length required is equal to 218.75 as per that formula. But what is the change is that here the weld is provided on three sides, right? One on the top and second one on the bottom, right? Second one is on the bottom, and as well as the third one is this vertical weld. However, that vertical weld, right, depth is that length is equal to 75 mm. That is already the restriction, because it cannot be more than this width of this plate, 75 mm. Therefore 75 mm is already fixed. Therefore now I have to have that this is equal to 2 multiplied by LW1 2 LW1 plus 75. Therefore what is that length of this overlap required, right? Length of this overlap required, right? That is how I'm just overlapping, right? This is how the called length of this overlap, either at the top as well as bottom. LW1 required is equal to, now it works out, say a value 71.88 students solving this, but however this should not be less than this 75 mm, right? Like this one, right? This 75 mm, right? Therefore it cannot be less than this width, right? This width of this flat, right? Therefore or say 75 mm, right? Therefore if I provide 75 mm overlap as well as at the bottom two overlaps of 75 and 175 in the vertical direction, then the total length provided is equal to 225 along with one end return here as well as one end return here. Therefore plus 10 plus 10 20. Therefore total length provided is equal to 245, right? Even neglecting that end return, I do have 225 mm, right? Therefore it is okay, right? Now let me show this schematic, this schematically, student, right? Just bear for a moment, right? This is how that schematic, student, right? Yes, exactly, right? This is how the flat is subjected to tension force, right? Whereas the welding is provided on the top, on the side, as well as on the bottom, right? Like this, on the three sides it is provided, right? On the three sides, right? On the top, on the side, and as well as the bottom. This is what called that overlap at the top, overlap at the bottom, right? That is how on the side, right? On the side I require 75 mm, right? This is how the schematic of this, and this is a gusset plate which is welded to a column or a member, right? That is how the gusset plate, right? This is how the gusset plate, right? Now whereas let us see the third bit of the same problem, student, right? What now I need to do is, if the welding is to be done on all the four sides, right? Therefore how on the four sides, right? Whereas the front I do have 1 2 3 sides, whereas on the rear side I do have one more side, right? One more side. Therefore two verticals, two horizontals, right? That one vertical is on the rear side, right? It cannot be seen, even I cannot see in this photograph, right? Like this, right? Just now we have seen on the three sides we have seen, but the fourth one is on the rear side of this, that will be seen as a dotted line, dashed line, right? This picture, right? Or even we can see this photograph, right? This is what on top and bottom. This is the schematic of on all the three sides. Now on the fourth side means that will not be seen on the rear side, like this. Now let me show this, right? On the rear side that will not be seen, right? Here on the rear side that will not be seen, right? Therefore however here we need to do the side welding. Therefore the partial safety factor for the side welding is equal to 1.25. Therefore now I would have the same formula, but because of this change in gamma mw is equal to 1.5, the result will change, right? Otherwise the formula is saying P is equal to Fu divided by root 3 multiplied by 1.5, where Fu is equal to 410, that multiplied by LW multiplied by effective throat thickness 3.5. Therefore now I'll get the length of the weld required, total length required is equal to 262.5. However, two sides of 75 mm we need to deduct. Obviously, the width of this flat is equal to 75. If I deduct 150 mm, hardly I have 112.5 mm. However, that divided by 2, it works out approximately 56 mm. However, this at the top as well as at the bottom cannot be less than this width of the flat 75 mm. Therefore, R side 75 mm. Therefore, the length of the overlap required is equal to 56.25 at the top as well as bottom, but that should not be less than 75 mm. Therefore, let us say 75. 4 75s will now work out 300 mm, right? 75 horizontal 2 75s and 2 verticals 75, right? One on the rear side and one on the front side. Therefore, total length provided is equal to 300 mm, whereas we require only 262.5 mm only. It is okay. Therefore, the design is safe. As shown in this schematic, student, right? That is how we'll provide 1, 2, 3, and on the rear side also. We'll provide that fillet weld. It is the fillet weld, student, right? Please see this, right? Fillet weld is provided. Therefore, I hope you understood this design, student. Now, if you understood, now let us move to the top. The next problem, student, right? A tie member consisting of ISA 80 by 50 by 8 mm, is of the grade Fe410 grade steel. It is of Fe410 grade steel. And just I am showing this ISA 80 by 50 by 8 mm, right? Is to be welded to a 12 mm thick gusset plate. This is the 12 mm thick gusset plate. Using the site weld, right? Because the welding need to be done at the site for this problem, right? Therefore, design the weld, right? Design the weld means how much of length of the weld is required at the top as well as the length of the weld required at the bottom. That is what we need to say, right? We need to design, right? That is how I'm just showing this, right? Actual photograph, depiction, student, right? Whereas the same is now shown schematically like this, right? These are the gusset plate, right? Angle, right? Front view and as well as the side view. That of the side view, right? Side view angle, right? This depth is equal to 80 mm. This depth is equal to 80 mm. Whereas this outstand is equal to 50 mm. However, that outstand cannot be 80 mm because if outstand is 80 mm, obviously it will undergo buckling and leading to the failure of this tension member. Therefore, generally the smaller dimension will be kept as the outstanding, student. You just remember this, right? This is important point, right? That is how in section, right? And its thickness is equal to 8 mm. That is what I am showing here schematically, which is connected to 12 mm thick gusset plate. This schematic side view I am showing as well as that of the front view. Front view is like this, right? This is of the front view, right? Connected to a gusset plate like this, right? That. However, let us see the design. You please see that this is carrying a tensile force, student, right? Obviously, once it is carrying the tensile force, right, then we need to propose the welding, one at the top as well as the bottom. Even we may sometimes provide the welding even at the side also. Just now we have seen the previous problem, right? However, what is given here is nothing is given. Therefore, now I'll provide the welding either at one top and bottom like this, right? Therefore, then these welds, though this member is subjected to tensile force, student, right? These welds will be carrying the shear force. The force in the weld is once again the shear force, right? Therefore, the governing force here is the shear force for this weld, right? Then now we'll see the given data, right? Fe410 grade steel is given. Therefore, the ultimate strength of the steel, ultimate strength of this steel is equal to 410 Newton per meter square, and yield strength or yield stress of the steel is equal to 250 Newton per meter square, and partial safety factor for yielding gamma m0 is equal to 1.1, and partial safety factor for the ultimate stresses gamma m1 is equal to 1.25. That we already know that data, right? And the site weld, for site weld, the partial safety factor gamma mw is equal to 1.5. Whereas if I go to these steel tables, or even I can go to SP61 1964 table for table for page number 12. Therefore, let me go to that. For ISA 80 by 50 by 8, I do have the area is equal to 9.78 and CXS is equal to 2.773. Let me go to that page number 12, student. Let me go to that page number 12. Just bear for a moment, right? Therefore, I am there in page number 12. Just for a moment, right? Just bear for a moment. I am there in page number now 9, right? Yes, 12, right? Therefore, this is ISA 80 by 50, 80 by 50 by 8. Therefore, for that, now I have to have this CXX, right? Center of gravity CXX is equal to, this is from SP. This is the table 4. This is the table 4 of ISI Handbook for Structural Engineer, or SP 61 1964, table 4, page number 12, right? Therefore, from that I am noting down this property, that the CXX is equal to 2.73 as well as the area of this angle is equal to 9.78. Therefore, once I note down that these are just I have noted down these properties, two properties, or this is equal to area is equal to 978 mm square and CXX is equal to 27.3 mm, right? Right? Now, however, since the section is welded, obviously, and it is subjected to tension force. However, there is an advantage of the welding, that the gross area itself is the net area. The gross area itself is net area. The other day you have seen in the previous video the advantage of the welded connections. There is a prime advantage, right? For gross area itself is net area. Then now I'll say, therefore, the design tensile strength of the angle I need to calculate due to yielding of the gross cross section, right? Obviously, the gross cross section will be yielding, right? Will be yielding when subjected to tension, whereas even the at ultimate load also I need to check, right? First, for the yield load or at yield stress, what will happen to the gross cross section if I see that? Now let me go to this page number 32 of IS 800, student, of IS 800, page number 32, right? This is a page number 32 of IS 8, right? 32 means 40, yes, right? That is how the we are there in design of tension member side. Design strength due to yielding of the gross cross section, TDG is equal to AG Fy divided by gamma m naught, right? Similarly, the design strength due to rupture, that of the plate, is equal to TDN, right? When it will rupture, right? When it will rupture means it is governed by the rupture at net cross sectional area, right? I don't have any net cross sectional area, therefore I am not using this, right? Therefore, even in such a case, TDN is equal to 0.9 AN multiplied by FU divided by gamma M1, right? However, I do have only gross cross sectional area, therefore I am just noting down this formula. TDG is equal to AG Fy divided by gamma M0. I am just recalling this formula and I am just substituting here. Right? Therefore, Fy divided by gamma M0 is equal to 250 divided by 1.5 AG 978 divided by 10 to the power 3. It works out 222.27 kilonewton. Means this one angle can carry 222.27 kilonewton tension force, beyond which it will yield, right? Or it will fail in yielding criteria, right? It will yield, right? Therefore, only here, because it need to be connected to a gusset plate, student, therefore fillet weld is only possible. Therefore, fillet weld need to be provided at the top as well as the bottom. Hence these are that just now we have seen that this outstanding leg is equal to 50 mm, and the leg which is connected to the gusset plate is 80 mm, right? 80 mm. However, just now we have seen that CXX is at a distance of 27.3 mm. Therefore, rest of the distance is equal to 80 minus 27.3. will work out 52.3 mm. Rest of the distance. Therefore, now I'll get how much of shear force need to be taken, or what is the reaction at the top as well as the reaction at the bottom, right? Assuming it to be a simply supported beam like this, right? A simply supported beam. Now I'm calculating how much of reaction will go at the top as well as at the bottom. Let those reactions at the top and bottom are P1 and P2 respectively, right? Therefore, let P1 and P2 are the shear forces carried by the weld at the top as well as at the bottom. Both are same, right? Therefore, now if I want to calculate this, now what I'll do is I'll take some of the moments about this point A is equal to 0. Therefore, by doing that, now I'll get P2 multiplied by that, right? P2 multiplied by 80 mm is a clockwise couple is equal to anti-clockwise couple is equal to 222.27 multiplied by 27.3 mm. Therefore, solving it, now you get P2. P2 means the force in the weld at the bottom is 75.85. However, by taking sum of the horizontal forces is equal to 0, now I'll get P1 is equal to 222.27 minus 75. It works out 146.42 is the shear to be carried by the weld at the top, whereas at the bottom it need to carry 75.85 kilonewton. Once I get these forces to, then I can easily calculate the overlaps, right? Therefore, if I go to this, just now we have seen from page number 78, class 10.5.3, 2.3. Here I do have the plate, right? The plate is let me see this data, right? 12 mm plate is given, right? 12 mm plate is given, whereas this angle is 8 mm. Out of these, 12 mm is the maximum. Therefore, even for 12 mm also, right? Even for 12 mm, just now we have seen that the thickness, right, is now 12 mm will govern. Therefore, for 12 mm, the size, minimum size should be 5 mm, right? Therefore, I'll use that data. Hence, now I'll say that, right? Size should not be less than 5 mm actually, right? Size should not be less than 5 mm, right? Then what now I'll do is right, this is how size should not be less than 5 mm, right? However, now let the size of the fillet weld is equal to 6 mm. That is my assumption. Therefore, even just now we have seen that from table 21, or for the fillet weld, that effective throat thickness is equal to 0.7 multiplied by S. Therefore, S is equal to 6 mm, right? That works out 4.2 mm, right? Therefore, now the load carried by the top weld is equal to P1, which is equal to 146.42 kilonewton, 10 to power 3 newton, is equal to the permissible shear stress in the weld, Fu divided by root 3 gamma m, right? However, here substituting which, now you get 410 divided by root 3 multiplied by 1.5, because this is the side weld, gamma m W is equal to 1.5 multiplied by length of the overlap required. Let length of the overlap required at the top is equal to LW1, that multiplied by TT is equal to 4.2. Therefore, length of the overlap required at the top is equal to 220.9. Similarly, doing that, the length, the load at the bottom P2, this load at the bottom is equal to P2 is same formula, right? That permissible stress in the weld, right, is equal to Fu divided by root 3 multiplied by gamma m, length of the overlap required LW2 at the bottom, that multiplied by effective throat thickness, right? Therefore, from this, only length of the weld at the bottom is unknown, right? Solving it, now I'll get 114.44 at the bottom, whereas at the top I'll get 220.9. Therefore, that is how I'll provide. Say, hence provide not less than, right? Even you can provide more also, right? Not less than, right? Therefore, or you may say, okay, 225 at the top and also at the bottom 115, right? Therefore, 225 at the top and 115 at the bottom, as shown in the figure, along with an end return of 2s, right? Where s is equal to 6 mm. Therefore, 2 multiplied by 6 mm. That is how the end return, right? Just now we already said, right? That is how the overlap, right? That is how the overlap, right? Like this. That is how at the top it requires 225 mm. At the bottom 114 mm along with an end return of 12 mm and 12 mm here, right? Both 12 and 12 mm as shown in the figure. Or I'll also show that schematically also, student, right? Let me once you understood that, let me show that schematically also like this, right? Exactly, right, like this, right? However, this is ups and down, right? Therefore, because I do have that overhanging leg at the bottom, whereas in my problem I have assumed at the top, right? That is how this LB, just now we got 215, and at the bottom, that was that short length, right? It was some 115 mm, right? It was, let me check that result, right? It was 114.44 and 220. Therefore, let us say at the bottom 115, at the top 225, 115, 225 respectively, right? Therefore, these are 115. Sorry, not this one, right? This is 115, right? This is 115 and this is 225 respectively. That is of the fillet weld, right? This is of the fillet weld in cross section as well as in front elevation. We can see that this is 225 length overlap, whereas even here 225 can be done, but it is of no use, because if you provide 115, that is sufficient, right? It can transfer that load, that's 75 kilonewton, whereas this can transfer the rest of that one roughly 115 kilonewton, 115 kilonewton, this 225 length, right? That is of the design. I hope you understood this design, student, right? Let us also see other schematics at a quicker pace, right? Let me go to that other schematic, right? Yes, right? This overlap just now we have seen, right? This is actually connected to a gusset plate, a channel actually. It is not angle, student, right? It is not an angle. This is a channel that exactly I am showing, right? There is how that overlap required at the top. Just now we got 225, even at the bottom just 115 mm, right? To a gusset plate. You can see this gusset plate is connected to the flange of a beam. A flange of the beam. Even it is connected by means of welding, right? Welding to the flange of a column stanchion, right? That is how these overlaps we calculated. This top overlap is equal to 225 and bottom overlap is equal to 115 mm. 115 mm. That is how the schematic, student. I hope you are right. Or another schematics like this, right? Therefore, this now we just got, right? This overlap is equal to 225 and this overlap is equal to 115. These are the different photographs, actual photographs, right? Actual photographs, right? Or even just now, I can show that in 3D view that this at the top it required 225, at the bottom I just required 115 mm only, right? This is a 3D view what I am showing. We are not doing the even I can do the welding on the side also, but I am not doing in this case, right? If more length of that overlap is required, then even you can do the welding on the side also, student. That advantage can be taken, so that the length of that overlap can be reduced. That's the advantage of reducing the gusset plate length. This gusset plate length can be reduced by reducing that length of the gusset plate. I can economize the section design also, right? Economize the section design, right? Whereas this you already seen in the previous case, right? Tension member when connected to a gusset plate using two sides as well as the three sides as well as four sides, that we have seen, right? I hope you are enjoying the discussions, right? Now this is also just now we have seen. Now let us move to the top of the third problem, student, at a quicker pace, right? This is the second design, student. Now let me go to the top of the other designs at a quicker pace, right? This is how the next design. The next design is design a suitable fillet weld to connect a web plate to flange plate and flange plate to flange cover plate of built up girder or built up beam, like this, right? Built up girder or built up beam consisting of, right, this one consisting of a web plate of 1000 mm by 12 mm, this one, right, 12 mm, and a flange plate of 400 mm by 20 mm, this one, and a cover plate of 375 mm by 16 mm, right? Then the girder is subjected to a factored shear force of 1500 kilonewton. This is subjected to a factored vertical shear force of 1500 kilonewton, right? Or even the horizontal shear force, because we know from strength of material that every vertical shear will have equivalent right complementary shear, horizontal shear also, right? Therefore there is also this also the horizontal shear also, right, which need to be resisted by these welds, right? Therefore we need to do this welding design between the flange and the cover plate, as well as between the flange and the web. These designs we need to do, right? And it is also subjected to a factored bending moment of 750 kilonewton meter, right? Use Fe410 grade steel as well as the shop weld. However, the basic assumptions of the beam designs are that the bending moment will be taken care by the flanges. Therefore, we are not designing these welds for bending moments, right? Therefore, we will only design these welds to carry a shear force of 1500 kilonewton. Please make a note of this, student, right? This is important, right? Therefore, we will design only these welds to carry 1500 kilonewton, whereas this bending moment of 750 kilonewton will be taken care by these flats. Sorry, these plates, right? These plates, these plate, right? This plate of 20 mm as well as this plate of 60 mm will be taking care of the movements 750 kilonewton, right? Please make note of this, right? Therefore, this is how the web is of 12 mm thickness and its depth is equal to 100 mm. That is how I'm showing the schematic, student, right? Therefore, you please see this cross section. I need to design these welds, right? Therefore, that is the given data that for Fe410 grade steel, Fu ultimate strength of the steel is equal to 410 Newton per mm square, and shop weld, for shop weld partial safety factor gamma m W is equal to 1.25 and Vu is equal to 1500 kilonewton and Mu is equal to 750 kilonewton meter. However, this Mu will not come in the designs. This is redundant data. We will not use that, right? And even from this IS 800 2007 class 10.5.7.1.1, just now we have seen that from page number 79. Page number 79. Let me go to that page number 79, student. A quicker page, right? That the permissible are the design strength of this fillet weld FWD is equal to Fu divided by root 3 divided by gamma MW. Therefore, substituting into that, even just now, even the previous problem also we have seen that, right? In the previous problem also we have seen substituting, which now I'll get, right? 410 divided by root 3 multiplied by divided by 1.25, it works out 189.37 Newton per mm square is the permissible shear stress in these welds, right? In these welds like this, right? Which will be provided in the longitudinal direction of this girder, right? In the longitudinal direction of this girder, right? Therefore, this is subjected to a shear flow or intensity of the shear flow. Therefore, it is subjected to a shear force. Like this, right? A shear force, right? Now, whereas I know that shear force in this weld, right? Now let us see that the very first connection, the connection of the web plate with that of this flange plate. This first design, right? And here you please see that I do have the thickness of that of the web plate as 12 mm and that of the flange plate is equal to 20 mm. Out of this, maximum is 20 mm. Therefore, just now we have seen from this table 21 for maximum 20 mm thick from page number 78 of IS 800 2007. Just now we have seen that the minimum size of the weld is equal to 5 mm, right? 5 mm like this, right? This is 5 mm, right? Therefore, from this, right, this is how that 5 mm. Once I see that if there is a minimum size should not be less than, whereas the maximum size also, just now we have seen the previous problem that it should be less than 1.5 mm, that of this 12 mm. Therefore, it now works out 10.5. Therefore, should not be less than 5 mm and should not be more than 10.5. Therefore, now let us assume the size of the fillet weld S is equal to 6 mm. Therefore, the effective throat thickness of this fillet weld is equal to just now we have seen this from class 10.5.3.1 page number 78, that 0.7 multiplied by S, or it is approximately 4.2 mm, right? However, these welds will be designed to carry only the shear force in these welds like this, right? Hence, let us calculate the moment of inertia of this welded plate girder. This is the welded plate girder about the centroidal horizontal axis. This centroidal horizontal axis XX, right? Therefore, now that works out. That works out, right? That of the web plate 12 multiplied by 1000 cubed by 12, right? And that of the moment of inertia, that itself is matching with the CG axis of this compound section. Therefore, I need not use parallel axis theorem. Whereas I need to use parallel axis theorem for the flange plates as well as cover plates, because they are far away from the CG of this axis. Therefore, now let me calculate. There are two such plates of 375 of 16 mm thick. Therefore, 375 multiplied by 16 cubed about its own axis, transferred to the CG of this compound section. 375 area, 375 multiplied by 16. Whereas h square, what is the perpendicular distance, is 500 plus 20 plus 8 whole square. Therefore, this 528 whole square. Therefore, transfer to the CG of this compound section, right? Plus that of this flange plate, right? Flange plate, right? There are two such flange plates. Therefore, 2 is outside, whose width is equal to 400 multiplied by 20 cubed by 12 about its own axis. Transfer to the CG of the compound section. Area is equal to 400 multiplied by 20 multiplied by h square. H is now 500 plus 20 by 2, 510 whole square. That now works out say 8.507 10 to the power 9 mm to the power 4, right? Similarly, the first moment of the area of these sections will now work out, say 375 multiplied by 16, which is at a distance of 528, right? That we have seen, right? Similarly, that of the flange 400 multiplied by 20 is the area which is there at a distance of 510 mm. Therefore, there is the area of the first moment of the area, which will now work out 724.8 10 to the power 4 mm cube, right? Whereas I do have the weld is provided on either side of the web, like this, on either side of this web, right? Like this, right? Here on this side as well as on this side. Therefore, the weld is provided in 2 rows, right? Like this, right? On either side, Therefore, it is provided in 2 rows. Therefore, the summation of the thicknesses that are provided is equal to sigma tt is equal to 2 multiplied by 4.2. Therefore, 8.4 mm is effective at that intersection of the web with that of the flange, 8.4, right? And the web is now the actual shear stress in the weld is equal to, we know that formula, VAY bar by IB, whereas here B is equal to summation of sigma tt. Therefore, substituting which, now we'll get say 1500 10 to the power 3 Newton, and AY bar, first moment of area, 724.8 10 to the power 4 divided by IXX. Just now we have calculated 8.5 10 to the power 9. Sigma tt is equal to 8.4. Now it works out 152.14 Newton per mole square is the actual shear stress, whereas we can permit up to 189.37. Therefore, actual shear stress is less than permissible shear stress. Therefore, the design what you have proposed with that of this 6 mm size of the fillet weld. Now this is how I'm just proposing with 6 mm is okay. This design of the connection between the web and that of the flange with 6 mm size is okay, is my conclusion, my inference, right? If it is okay, then what now I'll do is I'll see the next design, the connection between the flange plate and cover plate, right? This one, this second design, right? This flange plate and this cover plate, these two components, right? This design, right? How many mm, right? Now we'll do it a similar procedure, student. Now just now we have seen that let us here the load is small, student. Therefore, I'll reduce the size from 6 mm. In the previous case, we have assumed 6 mm. Now I'll reduce the size to 5 mm, or even you can provide the same 6 mm. It is left to you. But if you want to economize, you provide 5 mm, right? Therefore, the effective throat thickness TT is equal to 0.7 multiplied by 5, which is equal to 3.5 mm. Therefore, the first moment of the area will now works out. Now you please see that here 375 multiplied by 16 16, right? How much of shear is carried by these welds? Therefore, the intensity of the shear flow per unit length, right? Intensity of the shear flow per unit length of these welds perpendicular to the plane of the board, like this, perpendicular to the plane of the board, right? How much is the intensity of this shear force per unit length? I am calculating, right? Therefore, that now works out 375 multiplied by 16, or that much of area only. Therefore, there is a first moment of area. First moment of area, that which is there at a distance of 500 plus 28. Therefore, that is how it now works out. AY bar is equal to 316.8 10 to the power 4 mm to the power 4, and the summation of the thicknesses is equal to 2 multiplied by 3.5. It now works out, say 7 mm. 7 mm. Therefore, the actual shear stress using 5 mm size weld will now work out by substituting which. Now you will get V is equal to 1500 10 to the power 3 multiplied by AY bar has reduced to 316.8 10 to the power 4 divided by IXX will not change, 8.5 10 to the power 9 divided by summation of TT is equal to 7 mm. Therefore, the actual shear stress is equal to 79.8 mm, which is much less than the permissible value of 189.37 Newton per mm square. Even it indicates that even you can further reduce this size to even either 4 mm or 3 mm as appropriate. But even the code will not permit, because just now we have seen that minimum size of the weld, right? Minimum size of the weld as per the code, you cannot reduce less than 5 mm, student. Therefore, even you cannot reduce now. Therefore, that is how the Indian Standard Code will safeguard the designs, right? It will not suggest you less than that 5 mm, right? That is how the design of this welded plate girder, the connections between the web and the flange plate and that of the cover plate. Therefore, they are respectively 6 mm and 5 mm as shown in this figure. Right? Now, I hope you understood this design, student. Then, if you understood, then let us move to the top quickly. The last design. This is the fourth problem, student. Right? A 120 mm diameter bar. 120 mm diameter. 120 mm diameter. Round circular tube is to be and its thickness is equal to 6 mm, right? This tube its thickness is equal to 6 mm, is to be connected by a fillet weld to 40 mm thick gusset plate, like this. 40 mm thick gusset plate. I'm just showing this 3D view, right? It is subjected to a vertical factored load of right, like this, right? 4.5 kilonewton at 1 meter distance from the welded end. This is how that welded end, and a factored twisting moment of 1.8 kilonewton meter. Design the joint using shop welding. Use Fe410 grade steel. That is how the problem given, student. Right? Now, just I am showing that a 3D view of this schematic, right? That is how a plate, gusset plate, right, to which a hollow circular tube of diameter 120 mm or radius is equal to 60 mm is connected by means of fillet weld, like this, right? Fillet weld. Therefore, you design this fillet weld, right? And it is subjected to a concentrated load, like this, a concentrated load of 4.5 at a distance of 1 meter, like this, and as well as it is subjected to a torsion of 1.8 kilonewton meter, right? Therefore, design this fillet weld. How much is the size along the periphery of this circular tube, this circular tube, right? That is what the design, right? Now, let me show this schematically also, right? Then you will understand, right? Not this one, student. This is what I am trying to do the design. Not this one, student, right? Let me go to the schematic at a quicker pace. Yes, student. This is what exactly what I have shown, right? This is a gusset plate. This is what hollow circular tube connected by means of the fillet weld along the periphery of this tube. Therefore, what you design this fillet weld, or you design this fillet weld, right? Therefore, that is what the design. Right? I hope you understood now the 3D view, right? And as well as that of the schematics, right? Once you understood that schematic, student, you please see that this is subjected to one the direct shear due to this vertical load, as well as this vertical load is giving rise to bending moment. Therefore, this bending moment is also giving rise to the shear force in the welded connection, as well as it is subjected to torsional force. Therefore, this torsion is also giving rise to the shear, because there is a relation between torsion and shear. Therefore, that is a, now it is under the combined action of the direct shear, the shear second one, the shear due to bending movement, the third one, the shear due to torsion. Therefore, there is a combined effect is there. Therefore, let us calculate those, right? These are the given data, student, right? For FE 410 grade steel, you already know FE is equal to 14 Newton per square, and stop welding gamma MW is equal to 1.25, and radius of this tube is equal to 60 mm, right? That of this tube, right? This tube is equal to 60 mm, right? This is 60 mm, right? This is 60 mm, student, right? Therefore, once I know that, then also the data view factored shear force is equal to 4.5 10 to the power 3 Newton, and factored bending moment mu is equal to 4.5 into 1 meter distance. Therefore, that multiplied by 10 to the power 6, 4.6 multiplied by 10 to the power 6 Newton mm, or 4.5 kilonewton meter. As well as in the problem, it is already given that it is subjected to a torsional force, right? A torsion or twisting moment of 1.8 kilonewton meter, or 10 to the power 6 Newton mm, right? Let TT be the effective throat thickness of this fillet weld, right? Which I want to calculate now, right? That is what my design. Design the fillet weld means you propose the size and fillet size of that fillet weld, right? Now we already know from this class 10.5.1.1 already seen in the three problems that for the permissible shear stress in the weld is equal to Fu divided by gamma mw divided by root 3. However, gamma mw is equal to 1.25. It now works out 189.37 Newton per square is the permissible shear stress, student. Whereas it is subjected to a torsion. Therefore, I need to calculate the polar moment of inertia IZZ or IP, which is 2 pi r is the peripheral length multiplied by r square, 2 pi r cube multiplied by effective throat thickness. It is the polar moment of inertia of this weld, which is provided along the periphery of this hollow circular tube of thickness 6 mm, right? Then substituting the numerical values, I get this polar moment of inertia notated by IZZ or IP, or sometimes in some textbooks it is given by J, right? 135.7 to 10 to the power 4 multiplied by TT mm to the power 4, and the moment of inertia about the horizontal central axis is equal to that IZZ divided by 2. It now works out 67.86 10 to the power 4 TT mm to the power 4. Therefore, the shear stress due to the direct shear, right? This one, direct shear due to the direct shear is equal to the direct shear force divided by the shearing area. Shearing area is nothing but the peripheral length, total peripheral length of this along the periphery of this tube, 2 pi r multiplied by effective throat thickness. Therefore, if I substitute the numeric values, now I will get direct shear stress Fs notated by Fs is equal to 4.5 10 to the power 3 divided by 2 pi 60 multiplied by Tt. R side is 11.936 divided by Tt Newton per mm square. And what is the bending stress? Bending stress is given by Fb is equal to My by I or M by Z. Therefore, substituting which, now I will get M is equal to 4.5 10 to the power 6 multiplied by 60 divided by 67.86 10 to the power 4 multiplied by Tt, or say 397.93 divided by Tt Newton per mm square, right? However, this bending stress will be treated as shear force, because the failure of this weld is along the effective throat thickness. Therefore, hence the shear stress due to this third one, the shear stress due to the torsion or twisting movement is equal to Ft or tau, because T by J is equal to tau by R. Therefore, tau, the shear stress due to torsion, tau or Ft is equal to torsion multiplied by R divided by polar moment of inertia IP. Substituting numeric values, I'll get 1.8 10 to the power 6 multiplied by 60 divided by 135.7 to 10 to the power 4. It works out 79.57 divided by Tt Newton per mm square. I do have the three results. Therefore, the combined shear stress due to these three is square root of direct shear stress whole square plus the shear stress due to the bending Fb square plus shear stress due to the torsion, these three. Therefore, substituting these, now I'll get a square root of 11.936 divided by T2 whole square, 397.93 divided by T2 whole square, 79.57 divided by Tt whole square. That now works out, right? A numeric value, however, that numeric value should be less than or equal to 189.37. However, on the left hand side, I do have some result divided by Tt that should be less than or equal to 189.37. Solving which, now I'll get that Tt should be greater than or equal to 2.14 mm. Therefore, the size of the fillet weld should be S is equal to root 2 multiplied by effective throat thickness 2.14. Therefore, root 2 multiplied by 2.14, it works out 3.05 mm. Therefore, provide R side 4 mm. Therefore, provide 4 mm fillet weld. Just now, right, this. Therefore, you provide 4 mm fillet weld as shown in this schematic, 3D schematic, student. Or even now you can see that I am providing this 4 mm. 4 mm is the size of this fillet weld, for which the effective throat thickness is equal to 4 multiplied by 0.7. 2.8 is the effective throat thickness of this fillet weld, right? That is how the fourth design, student. I hope you enjoyed the discussions what we had in today's class, right? Therefore, if you have enjoyed the discussions, don't forget to click like, comment, share, subscribe our YouTube channel, right? Even thanks for watching. We'll meet in the next class with another discussion on the design of eccentric welded connections. Till then, bye bye, students.